we are going to go over electric fields. Now, if you remember from the previous section, we went over Coulomb's law. And Coulomb's law is force equals K, the charge 1, times the charge of object 2, over the distance between them squared. But we're going to rewrite this equation so we can apply it to electric fields. And we're going to rewrite it as K equals small charge times the object charge over the distance between them squared. So now we have force equals Q times K, big Q, over R squared. And we're going to take this right here, K, Q over R squared, and we're going to rename this E, which we're going to use as electric field. So the electric field is going to be equal to K, big Q, over R squared. So what the electric field represents is the force that a charged object is going to experience if it is placed near the charged object of charge Q. And this is going to be dependent on the object we place in Q's path, which is little q. So we're going to draw these electric fields for big Q. Here's big Q right here. Now, as you can notice here, R is the distance from big Q. So if R is very, very small, electric field is going to be large because R is in the denominator. So if the denominator is small, then the number becomes large. So we're going to draw points that are very close to Q. As you notice, the lines, the arrows, are actually pretty long. And these lines, the length of them, represents the strength of the electric field, or how large the value E is. So very close to Q, electric field is large. And as we get away from Q, as R becomes large, electric field shrinks, and we have smaller arrows, which gives us a lower magnitude. Now, I mentioned earlier that electric field can be used to determine what the force is going to be on a charged object in the field of the charged object Q. So we can simplify this equation, and we can make it force equals the charge times the electric field. Now, before we go into more detail, there are a few concepts I want to explain. And the first is the principle of superposition. And this states that electric fields are additive. That means if we have two electric fields that are right next to each other, they're going to add together. So if you have one going this way, one going this way, but at the same point, they cancel each other. But if you have two going in the same direction, they add together. One thing I didn't mention before, this is for a positively charged object, which is why the arrows are going out. But if the value is negative, the arrows point in. Now we're going to explain the principle of superposition in more depth. And we're going to use this using an example. So we're going to have a small negative charge. And we're going to have a positive charge that has twice the charge magnitude of this negative charge, which we're going to designate with two plus signs rather than just one, which the minus sign has. And we're going to draw the electric field for these two objects together. As you can see, the arrows are going out of the positive object and they go into the negative object, which I represented here and here. Another thing you should also note is that twice as many arrows are going out of the doubly charged positive charge compared to the singly charged negative charge. You're actually going to be tested on this most likely. And you need to note that the larger the charge, the more arrows you have going out of the object. Alright, so we got this concept down. Now I'm going to give you an example problem to make sure we know what we're doing. We're going to calculate the magnitude of the electric field at point B. And point B is going to be 2 meters to the left of a charge that has a value of 2 times 10 to the negative 9 coulombs. So we're going to draw this out, because it's always a good idea to draw out the diagram. Here's a charge for this right here, and it has a value of 2 times 10 to the negative 9 coulombs. And then we have point B, which is 2 meters away. And we're going to draw the field lines so we can understand what's going on here. So we have the field lines going out of the positively charged object. And now we're going to use the equation we discussed earlier, this one right here, because we're going to solve the electric field equation. So we have E equals K, Q over distance squared. K is equal to 9 times 10 to the 9. Q, the charge we're calculating the electric field around, has a value of 2 times 10 to the negative 9 coulombs. And the distance that we want to calculate from that charge is 2 meters. And we're going to square that. And we are going to get a value of 4.5 newtons per coulomb. Now these are weird units, but remember the equation I told you earlier. Force equals charge times electric field. Now think about it this way. Force we know has units of newtons. Charge we know has units of coulombs. And electric field, which we just showed right here, is Newton coulombs. So if you're doing the math, these two C's cancel out, giving us newtons equals newtons. So it makes sense.